All right, thank you everyone for coming to our final webinar of our 2025 spring webinar series. Today, Cassandra Brigham and I are very happy to talk to you about topographic differencing. OpenTopography has been working on developing these topographic differencing tools and resources for the past 7 or so years, and we're really looking forward to telling you about them today. And on the next slide, you will see an outline of our presentation. So the theme is topographic differencing, and we will begin by discussing vertical and 3D topographic differencing. We'll then discuss our automatic or on-demand topographic differencing workflow. We'll discuss errors in topographic differencing. We'll present a demo for how you can do topographic differencing on OpenTopography. And then at the end, we'll conclude with statewide differencing for Indiana.
So to begin with, I'll talk about how we do the topographic differencing. So we began with point clouds that were acquired at 2 different time periods. For all of the cases that we will discuss today, these are LiDAR acquired point clouds. You'll see that the younger point cloud at time 2 has a lot more points than the older point cloud at time 1, the compare point cloud. And one of the considerations for topographic differencing is that later data sets often have higher resolutions and lower error. The first point cloud shown in blue is the pre-event or compare point cloud. The second point cloud shown in pink is the post-event or the reference point cloud. We take the compare point cloud and grid it to a raster grid shown to the right. And then we take the reference point cloud and grid that to the same grid so that it has identical boundaries and resolution. The differencing comes in once we subtract those 2 gridded data sets. The difference is calculated by taking the reference and then subtracting the compare data set. And all of the differencing results that I've shown today, we've used the convention that blue represents upward motion and red represents downward motion. So you'll see cycling through 2 hillshades of DEMs taken of the Salt Lake City airport at 2 different time periods. And the map in color is the differencing map between those 2 DEMs. Red represents downward motion, blue represents upward motion. So you'll see that some of the planes are red and some of the planes are blue. Take a second and think about what does that mean? So if you think about it, the red planes are the planes that are no longer there between those 2 time periods, and the blue planes are the planes that have arrived. We can also represent natural change in differencing. So here we have 2 digital surface models, or DSMs, that have been taken in Yosemite National Park. The main signal that we see here is the big patch of red, which comes from trees being removed by a large rock slide. We can also see some smaller scale changes in the foliage of the trees. So these are these smaller red and blue patches that come from probably seasonal changes in the foliage and the tree cover between those 2 captures. Differencing also reveals change in the built environment. So these are 2 DSMs taken in Salt Lake City in Utah. We can see buildings that have been constructed. And so the blue rectangles represent where those buildings have come up in the intervening time periods between the 2 captures. Now I'm going to turn it back to Chelsea to go over some 3D topographic differencing.
Thank you, Cassie. So the other main type of topographic differencing is 3D differencing. And this plot shows results from the 2016 magnitude 7 Kumamoto earthquake in Japan. And you see in the figure on the right a bunch of arrows with circles. And these resemble GPS displacements, but they are in fact measured from topographic LiDAR differencing. And so the black arrow with the pink ellipse is the direction and magnitude of the horizontal displacement along with the error. And the colored dot represents the vertical displacements. And so topographic differencing shown here is conducted using the ICP, or iterative closest point algorithm, which is shown on the next page, the next slide. And in this method, we take windowed subsets of the pre and post event point cloud data, here shown in red and blue, and align them. So the video looks at moving that blue topographic data set and ultimately aligning it with the red topographic data set. And we do this alignment through an iterative approach of an affine transformation, which consists of a translation and rotation. And it's that net movement in 3D that we need to align those two point cloud data sets that is the ultimate 3D topographic differencing result. On the next slide. So we often get asked, well, should I perform vertical or 3D topographic differencing in my study? And the answer is that you should always, always start with vertical differencing for two main reasons. First, most change on the Earth is vertical. So vertical differencing makes sense. Examples include erosion deposition along rivers, coastal processes, earthquakes, landslides, cliff collapses, volcanic eruptions, urban growth, and changes to forests. Also, with meter scale topographic differencing, we can really get a sense of the type and size of errors that are present in the data and how they may impact our differencing results. And Cassie will tell us much more about that later. 3D differencing is a much more niched type of differencing and really only applies when the landscape shifts laterally, for example, due to tectonic motion in an earthquake or along a creeping fault, from a creeping landslide, or from sand dune migration. So past few years at OpenTopography, we've been working on developing on-demand topographic differencing. And the idea of this is that with a few mouse clicks, users can run vertical and 3D topographic differencing analyses on OpenTopography. So we developed this for a few reasons. First is that we wanted to standardize the approach to topographic differencing. We wanted to democratize access to topographic differencing tools, essentially make it so that beginners and experts alike could easily and efficiently do topographic differencing analyses, and wanted to solve common challenges such as coordinate reference system projections that are common in most differencing studies. Of course, we encountered several challenges. First, we wanted the differencing to work with legacy and hybrid data. So these data are going to have different resolutions, different quality, and could even be different type. For example, LiDAR and structure for motion data. The algorithms had to work on demand. So essentially, they can never fail. And they must be able to work with new data, the data that comes into OpenTopography, without additional customization. And the differencing algorithm had to work with the current cyber infrastructure and HPC resources already within OpenTopography. And if you'd like to check out more about our differencing workflow in OpenTopography for vertical and 3D differencing, I recommend that you check out that link below. The next slide shows examples of the topographic differencing results from the White Sands National Monument in New Mexico. The left shows the topographic hillshade. The middle shows vertical topographic differencing results, where red means downward motion of the Earth's surface, and blue is upward, red is downward. And then in the right is the 3D topographic differencing. Now, if you look just in the middle at the vertical, you can see how the sand dunes change shape. This does suggest motion towards the northeast of the sand dunes, that migration towards the northeast. And that is then captured also in the 3D topographic differencing results. And so this next slide looks at where you can conduct topographic differencing in OpenTopography. So to conduct topographic differencing, we do need overlapping data sets. And so these slides show coverage of these different types of data. And where the color is darker, so where there's dark green, that's where that's where there are overlapping data sets and where you can do topographic differencing. And currently, we only have differencing implemented within each data type. So you can conduct differencing within OpenTopography data sets, or you can do differencing between 3DEP and other 3DEP data sets, or between NOAA and NOAA data sets. And there's also many examples of differencing in New Zealand. In total, in the US's lower 48, there are over 3,000 data sets that have topographic differencing implemented, and these collectively cover at least 20% of the US's lower 48. And again, there's many examples in New Zealand, and collectively, these overlapping data sets record many geologic and anthropogenic processes.
All right, so I'm going to be talking a little bit about efforts we've made recently to make an on-demand uncertainty tool in OpenTopography. So let's start with a little exercise in trying to distinguish real change from uncertainty. So here we have an example of vertical topographic differencing from Northeast Virginia between a data set from 2012 and a data set from 2019. So what's being differenced here are digital surface models made from those point cloud data sets. So we can see areas in red on the topographic differencing map where trees have been clear cut. We can see areas in blue where trees have been replanted and grown. Areas in white are shown are areas of no change. Notice that this color map, which is computed with kind of the second and 98th percentiles, so it kind of includes most of the values, but not the extreme values for this map. It falls within about -15 to +15 meters. So we're on kind of the decameter scale here. Now let's go over to the same area, but only ground return points have been used to make digital terrain maps, or DTMs. We can begin by noting some natural change, so we can see the river incision and aggradation. We can also observe anthropogenic change, so the creation of building sites over here. The change shown here is an order of magnitude smaller than the change displayed in the differencing map of the DSMs. So at this scale, the areas of no change identified in the DSM differencing map appeared to have experienced up to 10 or 20 centimeters of uplift here in this differencing map. In fact, the whole map displays kind of a large scale pattern of uplift or of upward motion or apparent uplift. This leads us to the question, is this true change or is this error? Given that we are in kind of Virginia, this is 10 centimeters of global upward motion realistic? If it is error, how does this affect the magnitude of the differencing results and our overall interpretations? So let's delve a little bit into the properties and the spatial patterns that we could see of error. So to get your eyes used to the patterns that you'll be seeing, I've kind of made some squares that are representative of rasters. So let's define some terms. So systematic error is error where each raster cell has the same amount of error applied to it. So every single cell has the same amount of error. It's the same across the entire raster. Um, Once we get into random error, it becomes a little bit more complicated. We have two types of random error. We have spatially uncorrelated error. And so that means that the error in the raster cell, in one raster cell, is not related at all to the error next to it. It's completely independent spatially. But if you have spatial correlation, that means that error between two raster cells interact somehow, are related somehow. And that correlation can happen at different lengths. And so we call those correlation ranges. And these squares here kind of show you what different correlation lengths might look like. So we're going to go, again, from systematic to these very small scale to spatially uncorrelated error, but show you LiDAR pieces of what this might look like. So systematic long-range error that we find in LiDAR typically looks like this. So this is a particularly kind of egregious example of vertical differencing results from data sets with incorrect metadata. So this type of error manifests as an apparent vertical change across our data set with systematic changes ranging from a few centimeters. And so that stems from the reporting of an incorrect geoid to tens of meters, which stems from the confusion between ellipsoidal heights and orthometric heights. So in the upper right corner, we have an explanatory diagram. So elevations are often reported based off of a reference ellipsoid, and sometimes it's useful to know an elevation relative to a geoid, which is a hypothetical ocean surface, and there are different geoid models. The height to the surface above the geoid is termed the orthometric height. In the lower right corner, we can see how these larger scale errors arise when you mistake the ellipsoidal height for the orthometric height. And again, this comes from metadata misreporting. So these are errors in the metadata. We also get flight line errors, and so this is happening at the range of about a kilometer to hundreds of meters. So airborne LiDAR surveys are typically conducted along multiple parallel and overlapping paths or flight lines. And they are due to georeferencing errors uh, from the equipment in the plane. They make these swath-to-swath artifacts of about 10 centimeters or less, and they can really interfere with linear patterns of real change that you see in the differencing areas. Accurate vertical differencing results require that the topographic data sets are well aligned, or in other words, are correctly georeferenced. When the horizontal georeferencing errors are present, a topographic feature in one data set is offset from itself in the other data set. So this is shown in the schematic here. So here's an example of two data sets that are well aligned. So when you difference T2 from T1, all of the topographic change that you are measuring is real change. So the real and apparent change are the same. However, if you add alignment error and then you difference T2 from T1, you show that the area where the topographic peak is mapped is in a different location, and you get this strong signal that is correlated with the slope or with the landform aspect. And this can really mask the signal of real change in your topographic change results. And so right underneath, we have the magnitude of the vertical error that comes with this vertical displacement error. On the shorter range of potential LiDAR errors, we have misclassification errors. So this comes from when you move from having a DEM of classified points and you want to make a bare ground model. When you just select the ground points, sometimes those ground points are not correctly classified. And you also have some perhaps vegetation or building points thrown in there as well. And so the lower left example shows you what those artifacts might look like. And those are happening at the range of meters or tens of meters. Geometric distortion happens when when the LiDAR sensor is oblique to the ground surface, and it can lead to greater horizontal displacement errors for each point in the data set. And it affects the precision of the elevation data, particularly in areas where there are steeper slopes. And so the diagram in the upper right corner shows you how uh, two, if you have the same kind of flight paths over two areas, you can still get apparent uplift due to geometric distortion. And the topographic change map of a cliffed area shows you that the geometric distortion signal lines up very well with the slope map. Now that we've cataloged some of the types of errors present, let's think about how we'd go about quantifying their effect on vertical differencing results. For very long-range errors, that is, errors that are almost perfectly correlated at the scale of our area of interest, we are interested in the vertical bias, that is, the vertical alignment error that should be close to constant across the raster. For spatially correlated errors at the long, mid, and short scales, error magnitudes will change across the raster. So we want to quantify the mean correlated uncertainty values over 3 scales. To do that, we can model short scale, mid scale, and long scale correlation patterns of the differencing results. We can also account for uncorrelated random error at very short range, but computing the mean uncorrelated uncertainty across the area of interest. We can propagate the mean correlated uncertainties computed for each correlation length scale and the mean uncorrelated uncertainty into a total mean uncertainty for the area. So it gives us two values at the end of our error analysis, a vertical bias value and a mean uncertainty value. So let's apply this to this example that is taken from just southwest of Indianapolis. It has a very strong flight line error signal, along with some true change happening in some of the farmland. So let's start by calculating the vertical bias. So if we take all of the values of change, which we consider, given that we need to make this tool automatic, we can't actually decide for ourselves what is real change and what is error. So we just assume all of it is error. If it's a large enough area and we have a large enough number of observations, we expect the distribution to be normal and centered on 0. Any offset from that normal, or any offset from 0, we can attribute to vertical bias. So looking at this example, we find a vertical bias of -3 centimeters. Then let's move on to the mean correlated uncertainty. So again, we want to find those characteristic correlation lengths of the uncertainty, especially at the different scales of uncertainty. For that, we're going to use a tool called a variogram. So variograms are a tool in geostatistics to explore the spatial relationship between data points and how that changes over distance. The variogram is defined by the variance difference between data values at two locations, plotted as a function of the distance between those two locations. So this is an example of the variogram of our location, Indiana. So on the y-axis, we have the semivariance. So again, the kind of proxy for the amount, how different two raster values are. And then we have the lag distance, which is the separation distance between those raster cells. Sorry. The red line shows you the first correlation length, the first correlation range. And the second line, the green line shows you the second correlation range. And so we have correlation ranges at 22 meters and about at 1 kilometer. So we'd expect to see error patterns at those scales. So if we look back to our raster, um, again, we can see kind of the prominent road features that correspond approximately to the 22-meter scale. And the 1 kilometer scale corresponds approximately to the flight line error bands. So by taking those correlation ranges and then propagating it into an uncertainty value, we can get an uncertainty value for this area. And that gives us about plus or minus 9 millimeters of uncertainty across the area. As the areas grow larger, you're going to be kind of averaging out your uncertainty, so your uncertainty values will get smaller. All right, so I'm going to show you a quick demo on how to how to do differencing for yourselves on OpenTopography. Oh, all right. So you're going to navigate to opentopography.org and go to your data map. So again, you can difference between data sets of the same type at the moment. So these are the OpenTopography hosted data sets. These are the USGS data sets. And these are our NOAA data sets. And so you're going to be wanting to look for data sets that overlap. And so if you can see here, there are areas with lighter green and darker green. And so we're going to try to find an area where we have an overlap with this darker green. So let's focus on one spot along the coast in the Florida Panhandle. So you draw a box over your area of interest, and then you go to the high resolution topography tab. So all of the data sets that are available for differencing will have this button available. So I want to take a look at how a difference between Hurricane Michael in 2020 and let's say data from 2007. So I'll click the differencing on my desired compare data set, but it doesn't matter because you'll be able to change it once you get here. So again, it shows you your area of interest. Here it says I've selected too many points. You can access more points by signing up to OpenTopography, so that's definitely an incentive to sign up. You can also, right now it's showing you the number of points to create a DSM. I'm only interested in the bearer, so I'm going to select ground only. This will only return my bare earth points. And now all of a sudden my selection area is okay. So here I can select, once we're under vertical differencing data sets and coordinate system, here I can select which data set I want to use for differencing. So I'm interested in seeing the kind of effects after Hurricane Michael, let's say. So I'll choose this one. And so when you look here, it'll tell you what your compare data set is. So it's our 2007 data set. We have the acquisition date here. We have the horizontal coordinates of the original data set. OpenTopography will reproject this into the native UTM coordinates for the differencing. And then we have the vertical coordinates of the original data set. And so note here that they've included the geoid. So again, those are the different geoid models that I've mentioned before, that if the metadata is recorded incorrectly can create those systematic errors. On the reference side of things, we have the younger data set, that 2020 data set. It has the same horizontal coordinates and a different geoid. If you were referencing yourself, you would have to reproject and everything, the vertical coordinate system into the same geoid, but this OpenTopography takes care of that for you. Here you can choose your grid resolution, which will also determine the resolution of your differencing products. So we're going to stick with 1 meter. This is where you choose your error handling. So the approach that I was talking about earlier is covered under the estimate mean uncertainty using the geostatistical approach. So I'm going to check this box. If you have, if you know that your uncertainty is random and independent, kind of the random uncorrelated uncertainty, and it's at a certain value, and you know that you can't trust measurements below that value because you don't know if they're signal or uncertainty, you can also use a minimum level of detection. And so the minimum level of detection will, using this option, will mask all the values that are below that threshold value. All right, so here you would submit this job and wait. So processing for jobs below 100,000 is going to take you probably less than half an hour. If you process a job over 200,000 points, it'll more likely take you maybe an hour, potentially two if it's above 200,000 points. So the time of a lunch break or a French lunch break. I grew up in France. 2 hours is a nice healthy lunch break. So I actually have the results from here. And so from the differencing area that I was looking at. And so let's look at what those results will look like. So here we have the differencing products you can download. And so those will include the reference DEM and the compare DEM, as well as the differencing results raster that you can download. And for the visualization products, if you click on this, it will give you a high resolution map that you can view in the browser if you want to take a look at details on the of the differencing results. If this is the vertical bias estimate, so here it's at about -5 centimeters of vertical bias. And you can see the histogram that got to these results. And more details about the statistics of the distribution. Here is the raster of once you correct for that vertical bias. So you remove the vertical bias, and you can actually see some more artifacts created by error more clearly once you remove the vertical bias. So these, what look like kind of big ripples, are in fact artifacts. And this is the output for the for getting your mean correlated uncertainty values. So each of these lines is the representative correlation range that the model fit. And here you have the corresponding uncertainty values that are associated with that correlation range for your area. So we have 3 representative ranges for this area. So 23 meters, 220 meters, and about 2.4 kilometers. So if we look at our differencing results, we can kind of see where these numbers are coming from. So you have change on the order of tens to hundreds of meters that might be real change. So the creation of these channels, change along the coast, potential change in sedimentation along this area of the coast. But that 2.4 kilometer change, it obviously comes from this section, from this area of apparent upward motion and these 2 swaths of apparent downward motion. And so what's happening here is likely due to flight line error. And so our uncertainty modeling is picking up on that flight line error and assigning it about 10 centimeters, plus or minus 10 centimeters of uncertainty. So if you look over this area and you pick your uncertainty value, you'll have to give it plus or minus 10 centimeters. And when you're looking at here you're looking at differencing values of about 20 centimeters, that's going to make a bit of a difference. So if you're interested in, like, for example, coastal changes after the hurricane, that plus or minus 10 centimeters is going to give you important context. Another nice feature here, again, is the hillshade viewer. And so if you want to kind of sanity check yourself for some of these changes, I often go down to the hillshade viewer and take a look. So here you can see some of these channels that have been formed and some of the coastal differences as well. All right. That's it for the demo. Let me bring it back to Chelsea. 1 second.
One slide back. So the next part of this presentation, we're going to discuss a big project that we did a few years ago where we conducted topographic differencing at a meter scale resolution of the entire state of Indiana. So on the next slide, so what was motivation for this project? So first we wanted to figure out how to do large-scale topographic differencing. And we anticipated that there would be different challenges going from the kilometer to a few kilometer scale versus the entire state of Indiana. And second, we were also interested in what a decade of change looks like across an entire state. And Indiana is very interesting because they have many different types of change, both from natural environment as well as anthropogenic processes. And this figure here is looking at an example of two different topographic hillshades at the Indiana Dunes National Park. And so we picked Indiana on the last slide for a few reasons. First, at that time especially, it was the only state with two statewide data sets. So Indiana was an obvious choice for this project. And there are more data sets now that do cover more and more of states, but I believe it is still the only state with this full statewide coverage. And second, we anticipated a variety of interesting types of change. And then third, OpenTopography has been in a data hosting partnership with the state of Indiana. And we wanted to do this exercise to continue to develop that partnership. So on the next slide, of course, there were many challenges that we faced in this part of the project. So this is a big data project. So the full area of Indiana is really 2 to 3 orders of magnitude larger than even the area in past large differencing studies. And this big data aspect brings several challenges. First, we really need to use efficiently high performance computing resources. Second, the algorithm has high memory needs, and this was especially for the step of gridding the point cloud data to rasters. So we had to figure out how to develop that algorithm to use the memory efficiently. And then the final products are 4 terabytes. So we thought a lot about how to make the results easily accessible to the general public, and I'll discuss that more later. Of course, there's noise, as Cassie has told us about. As we did this project a few years ago, and we ultimately decided not to correct the noise, but we did deeply think about what are the noise sources at that statewide scale and how can we think about them. And then, yes, we also thought a lot about how to visualize the results. Next slide. So here's the statewide topographic differencing results for the state of Indiana. On the left, you can see the digital terrain model, and on the right, the digital surface model. And this is change from about 2012 to 2018 on average. On the digital terrain model, the signal that comes out most are those north-south and east-west lines. And these are those flight line alignment errors that Cassie had talked about. On the DTM, we also see examples of fluvial change from the different rivers in Indiana, as well as signals from quarries and mining, particularly in the southern part of the state. The right shows the digital surface model, and there we do see a larger signal from the rivers and riparian zones. And we also see quite prominent changes in vegetation. So in the bottom middle, it goes from purple to red, and that reflects the data sets being collected at different time periods. And so this shows a seasonal change in the vegetation. So I'll discuss a few examples now of Indiana. The first one is looking at human-induced change. So the top is the development, a new development in a suburb of Indianapolis, where all those blue rectangles in the top right are new houses that are part of that suburban development. And then the bottom example shows the development of a cloverleaf intersection along a highway. This example is looking at natural change. So these are sinkholes, and these are in sort of southern central Indiana. And the red represents downward motion of the Earth's surface. So that's sinkholes that formed between the two acquisitions. And then blue represents upward motion of the Earth's surface. So sinkholes that were filled in. And so here, let's see if you can press the video. So this is looking at visualization that we made of the topographic differencing results of the state of Indiana using a GeoServer. And so this is shown in real time. You can go to pearl.opentopography.org/Indiana, and you'll be able to see the topographic differencing results. So we previously were looking at the topographic change from both the DSM and DTM, and now we are zooming into part of Indianapolis, where we can zoom in and see detailed change. And again, we developed this because those 4 terabytes of data, it's hard for people that aren't part of the OpenTopography team to really think about how to use and visualize that data efficiently. But people can come to our website here and explore this change in Indiana. And so here we're looking at these blue rectangles, and this shows positive change of the Earth's surface, looking at the DSM, digital surface model, and this represents the building of a new set of warehouses between the 2 acquisition dates of the LiDAR. Here's new buildings or suburban development. And again, you can look, you can use that legend to see the different topographic hillshades of the DSM, the DTM, and the differencing results, as well as the canopy height model. So that's the end of the discussion about Indiana. I wanted to highlight a few more resources in the last part of our presentation. So we have developed quite a few sets of self-paced resources. So if you want to learn more about topographic differencing, we welcome you to check out these pages with the link there. So that link provides range of blog posts with differencing examples, as well as a blog post about error in LiDAR topographic differencing results. We provide videos that will walk you through how to do differencing on OpenTopography. And we also have 3D topographic differencing. We have a video that shows you how to do 3D differencing using MATLAB. We have conference presentations. We have GitHub links to differencing code for vertical and 3D differencing. And we also have an undergraduate differencing exercise where the students look at topographic change from a make-believe but realistic earthquake in Salt Lake City. And I wanted to point you out to these two publications from the OpenTopography team. They're both open access. The one on the left is from Geosphere, and this paper is detailing that on-demand vertical and 3D topographic differencing workflow that we developed and goes into more detail about some of the different challenges that we faced and solutions that we implemented on OpenTopography. And then the paper on the right references this project looking at the statewide change for Indiana. So that's our presentation, and we wanted to thank you all for coming today to our last webinar of this series. And we have about 13 minutes left, and it'd be great to use this time to answer any questions that you have. So you can either raise your hand, we can unmute you, or you can put a question in the Q&A. You can also feel free to ask questions or perhaps directly what we talked about, but maybe you're thinking about doing topographic differencing for your own project and you're interested in how to get started. So we'd be happy to help you with that right now as well. Will you provide this recording and or references? Yes. All of our recordings are available on our OpenTopography YouTube channel, and they're also linked to the news item about the webinar series. And for references, I suggest that you look at that page there with the different resources. OpenTopography, or that page with OpenTopography's resources on differencing, as well as the paper publications. Ben asks, if you are looking at coastal data sets, how do you account for changes in sea level due to tides? Talk about that. Do you have more insight maybe than I do on that one, Cassie?
I guess, I mean, our vertical differencing tool does not take it into account. So uh, it's kind of, if you were interested in accounting for that, you would have to kind of go about your first process. You could use us as kind of an exploratory tool, and then do your own analysis.
Yes.
Because
We
you'd
did
be
provide
changing kind of your reference rather than the global. Yeah.
we do have many data sets for differencing along coastlines, particularly, well, the West Coast near San Diego and different parts of the East Coast. So there is quite interesting differencing that could be performed along the coastline. Someone asks advice on alignment of SFM data sets without ground control. So there's different ways of doing this, and a very quick way is to add your own synthetic, or basically your own ground control. And so to find areas that are stable, it can be well identified on both data sets. So for example, the intersection of a road that you're quite sure didn't change. And then to find many of, or yeah, so to use those as markers, but then to find as many of them as possible along different like segments of the area. So you wouldn't want them all to be within a line. But ideally they'd be a cross or maybe more of a circular shape to provide that linking or alignment between the two data sets. And there's also more advanced methods that look to align with the elevation or with the slope. And Cassie's been looking at some of those recently. I don't know, or Cassie, could you talk about that a little bit more?
Yeah, so I'm looking at it in the context of so one of the um, ideas is behind kind of a lot of these uncertainty measurements is that some of the statistical properties like the mean and the variance don't change across a data set, but oftentimes they do. And so when you're trying to account for that, you are trying to find explanatory factors, so like slope or vegetation. And if you add that into the equation in your analysis, then you can get better fits for uncertainty and also better fits for corrections.
Tegan asks, if you are an educational member, is the OpenTopography account free to set up in order to download larger point data sets? Um, yes. So yeah, so everyone can make a free account on OpenTopography. And if you are an educational member with an EDU email, you get access to all of our resources. If you're an educational member without an EDU member or without an EDU email, you get access to many of our resources automatically. You can write us an email and an application for access to the 3-dep data, which cover now the majority of the US. And depending on what you want to do with those data, you can then download 250 to 350 million points at a time. And if you really want bulk data set, I want to get into a little bit more processing techniques, you can do bulk downloads.
Seems like Matt has helpful advice on the coastal question.
And one thing new advancement we're looking to soon is to do multi-temporal differencing. So how to do differencing of areas with, say, 5 to 20 data sets, which most often occurs along coastlines. Like people.
I'll just say one more thing that related to Ben's follow-on question to Matt about the sea level thing is compares differencing across catalogs. Currently, you can difference within 3-dep, you can difference within NOAA. But one of the things we are working on is being able to take a data set from a NOAA catalog and compare it to a data set from 3-dep. Maybe Matt was typing that. But I just wanted
Yeah,
to
thanks, Chris.
clarify
I was in the
that's
middle of typing that.
yeah, I thought maybe you were, but I thought I'd just say it because it's easier. That's a piece of this puzzle is sort of the intercomparison across these different catalogs, but there's a variety of reasons why that's technically complicated and we haven't gotten there yet. But it's coming. But in the interim, Ben, your plan sounds pretty good.
Harry asks
Uh,
if we compared USGS quality level 1 with quality level 2 data sets.
So just in the nature of how 3-dep acquisitions have been going, I've mainly been comparing um, quality level 3 with quality level 1 or 2, because all of the first acquisitions tend to be the older acquisitions, so it's QL3 or older, with no quality levels. I would love to be able to compare those younger ones against each other. If you know of any sites where there are, I mean, I know some QL2, QL1 sites. I haven't done kind of an extensive error analysis on those yet, but that is my plan. If you know of any QL0, QL1 sites or QL2 sites, that would be very interesting too.
And the Indiana might be an example, certainly an example of differencing QL levels. And that's an interesting case because the flight line errors that are quite prominent in the DTM differencing results correlate with the acquisition geometry of the earlier data set, which isn't surprising, but does really highlight how LiDAR data quality is improving over time.
Yeah, and
We've
I'm
done
just to follow up on that one as well. I'm looking at the QL level specs for USGS, and your QL0 is a 5 centimeter vertical accuracy, while QL1 and QL2 are 10. So I'm just curious. It'd be interesting to know how that actually pans out in reality, as Cassie was saying.
Well, and the accuracy of the individual DEM is not necessarily going to be the accuracy of the differencing product itself. So yeah, it's
You've done differencing with Arctic DM. I have not. Has anyone here done that?
I have not.
No, and I would say that the complication with the Arctic DEM is these are photogrammetrically derived topographic data sets from commercial imagery, optical imagery. And the mosaics, you can get an Arctic DEM mosaic, and it's available through OpenTopography. Those are composited over considerable amounts of time. So there's a significant time variation within that data set. They also provide the strips, which are the individual DM, some sort of time coherent imagery. And so if you were doing differencing, I'd want to look at the strips, but the problem is the strips are these little bits and pieces, so you sort of have to manage them. We haven't dug into managing or accessing the strips of Arctic DEM data, but that would probably be where you'd start.
I was
I did
pointing out
some
some
differencing
examples.
with Arctic DM years ago on some fault scarps in Iceland, and I was comparing against SFM data I collected. I struggled with some artifacting, but I would be interested in revisiting that.
I was pointing out some examples of different quality level data in New York State. Thank you.
Oh yeah, thank you.
All right, well, thank you everyone for attending our final webinar. And you're welcome to use any of these social media and then our email, info@opentopography.org, if you'd like to get in touch with us in the future. And again, all of these webinars are recorded and will be available on our YouTube channel. So thank you for coming.